The reliability of a consensus is not the size of the consensus, but the frequency with which such a consensus has in the past turned out to be true over time.
Hi, this is John Loftus, and you're watching Atheist Edge.
Okay, so at the beginning of each week, you're given 3 challenge questions to test your comprehension of the week's reading assignments. Dr. Carrier evaluates these personally and responds to them with what I can only describe as meticulous detail. Before we dive into some numerous examples, I would like to emphasize that this video series is in no way meant to be a substitute for actually taking the class yourself. Your journey will undoubtedly be different than mine. All right, so let's get into it. I'm just hitting the high points here. There was much more to this course than what you're going to see in this video series. I'm not starting in any particular order. So the first challenge question we're going to look at is the following. Dr. Carrier writes, in my advice on probabilistic reasoning lecture, I noted many words we commonly use that conceal probability judgments, as opposed to words like odds or probability or frequency, which don't conceal it so much. I mentioned as examples normal, abnormal, and strange. Other examples are usual and unusual, common, commonplace, and rare, expected and unexpected, exceptional and unexceptional, typical and atypical, also strange, weird, and bizarre. So the challenge question is, give as many examples as you can think of off the top of your head of words other than these that you might often use that actually constitute judgments about probability. My response is as follows: aberrant, outside the norm, outlier, minority opinion, overwhelming expert consensus, baseline, standard, and speculative. These are terms that I use often when defending or refuting a claim. Admittedly, I sometimes use these terms based on my fallible memory, invalid data, or outdated data. Dr. Carrier's response: those are good examples. Some of these call up the distinction between frequency and probability. Aberrant, for example, means of low frequency, which does not mean of low probability in the sense of selection. But that does not automatically mean epistemic probability. What you are proposing is aberrant. Therefore, what you are proposing is improbable. Because evidence can change that, it may be true as a prior probability. If you are proposing an aberrant explanation of something, your explanation does start less probable than a less aberrant explanation. But if evidence stacks up for your aberrant explanation, then it can become probable, while remaining aberrant in the sense of frequency. For example, he got rich by winning a lottery is an aberrant explanation of someone getting rich. Most rich people did not get rich that way. But if all the evidence points to that being how he got rich and not some other way, then it is probable that he got rich by winning a lottery, while it remains also true that few people get rich that way. Then the way he got rich is aberrant, rather than it merely being an aberrant explanation. Keeping distinct of these things is important to critical thinking. A really good example you brought up is the overwhelming expert consensus. That is a frequency statement, most scholars versus few scholars, but it does not automatically correlate with an epistemic probability. That almost all scholars conclude X does not entail X is highly probable, but it does count as evidence for that conclusion. In particular, the epistemic probability, the probability that X is true, is not the probability of encountering a scholar who thinks that, e.g., if 99 out of the 100 think that does not mean the claim is 99% likely to be true, but the probability that a strong expert consensus is true, which will be the frequency of such an expert consensus turning out to be true. So if in a field like, say, history, where the expert consensus gets overturned a lot, the probability that an expert consensus position is true is going to be not so high as in a field like, say, physics, where the expert consensus, when very strong, does not get overturned at all. In fact, it is historically remarkable and often becomes the stuff of legend, even if the strength of the consensus is the same. For instance, that 99 out of 100 historians think X, it may be that X is only 95% likely to be true. Whereas when 99 out of 100 physicists think X, it may be that 99.9% likely to be true. The reliability of a consensus is not the size of the consensus, but the frequency with which such a consensus has in the past turned out to be true over time. Then, of course, you can show that a consensus is ill-formed. It is not soundly based. Then it no longer can carry the reliability of a well-formed consensus. If 99 out of 100 nutritionists hold a demonstrably ill-formed consensus, the probability that that consensus is true may be quite low, say even 30%, if 2 out of every 3 ill-formed consensus positions held by nutritionists in the past have been overturned or abandoned. Whereas if the same frequency, 99 out of 100 nutritionists, hold a demonstrably well-formed consensus, then the probability that that consensus is true may be quite high, say even 99.9%, if only 1 out of every 1,000 well-formed consensus positions held by nutritionists in the past have been overturned or abandoned. So the moral of the story is this: when using words that denote a frequency, make sure you know A, what it is a frequency of, and B, whether that is the relevant frequency for what you mean to argue. And the start is to always be quick to recognize when you or anyone else is making such an assertion about frequency, and especially when that assertion is being used to argue for an epistemic probability. What is the logical relationship between the frequency asserted, e.g., that something is an outlier or conversely is standard, and the epistemic probability being assumed? Does the thing being an outlier or standard mean that it is probably true? And if so, how does it mean that? The only thing on your list I have to pull out is speculative, which is not typically an assertion of frequency, but of epistemic weight. A speculative explanation is typically one without confirming evidence. Otherwise, speculative explanations can far outnumber confirmed explanations. So their frequency, whatever it may be, won't relate to their probability. For example, the probability of your running into a speculative explanation of something online is high, but the inherent probability that any such speculative explanation is true is low. The best course of action seems to avoid, as much as possible, the use of modifying adjectives, for example, strange or unusual, and rely on the facts. And then at the end, Richard recommends some follow-up reading on evaluating arguments from consensus, shown here. The next challenge question deals with how graphs and charts can be manipulated, and it's from the reading assignment in Access Shenanigans. This was my response. It took me a while to make heads or tails of these graphs due to there being two different values on the y-axis. Now I see that the values on the left only apply to the black line, and the values on the right only apply to the shaded line. I was originally trying to get both lines to somehow apply to both values. This method might be preferable to show comparisons, but I think two separate graphs side by side would be less confusing. And here is Dr. Carrier's response. That is, of course, Levitin's point. When graphs are presented this way, lies can be told, or results hidden from view, or arbitrarily fabricated, etc., by changing one of the scales. Those two graphs are the same data, but with different scales on the gray y-axis. The first was an actual graph used in Forbes. The second is Levitin's creation using the same data and graph, but just changing the gray y-scale to prove his point. We do need these kinds of graphs, as the goal is legitimate. For example, to see if increasing expenditures on students results in increasing SAT scores, you have to place each graph next to the other to see if they align or diverge. The trick is that the scale used on every side has to be meaningfully selected, not chosen in a way that would skew or conceal results. The question is thus whether an increase from 840 to 900 SAT is worth spending an extra $1,000 per pupil, which is a policy decision. But one won't even see that as an option in the first version of the graph, as the scale chosen hides the bump in SAT scores, making it look non-existent. One can also question whether year is even relevant, and that may be what you are interested in. A simple graph of money spent to average SAT score regardless of year, simply replacing the x-axis with the black y-axis and having only one line may be more useful, but that's an epistemic choice. It depends on to what extent year matters. But the lesson Levitin is using for this is to watch out for scale distortion when graphs are used to present data, which is especially true for double Y graphs, as you noticed, but is still true for any graph. The next challenge question deals with using 1 and 0 and all the possible numbers in between to calculate a correlation. This was my original thoughts on it. I've known that 1 means the strongest possible correlation, but I always thought that 0 meant no correlation at all. Is that correct? Also, I've never seen a negative number represent an inverse correlation, but that makes perfect sense too. What I can't wrap my head around is this. How did they arrive at a 0.91 correlation for the data in the graph? And what is the mathematical formula for determining the actual value? Whatever that equation is, I'm thinking it would be useful for a good skeptic to memorize it. Dr. Carrier's response. Calculating the correlation factor is tricky math. One would need a course in statistics to get the full ins and outs. So that's not an option for most people who still need to critically think this stuff. Levitin does explain in his book that correlations range from -1 to 1, and a 0 means no correlation. A -1 would mean a perfect negative correlation. For example, more money spent lowers SAT scores, with such reliability as you can count on always to be the case. With a correlation of 0.91, what this means is that 91% of the SAT score increase can be credited to the spending increase, with a 9% random variation in SAT score unconnected to money spent. Note that correlation just means as X goes up, Y goes up. A negative correlation means as X goes up, Y goes down, or vice versa, which doesn't tell you the degree. For example, you could have a 0.91 correlation between money and SAT scores, whereby every added $100,000 per pupil results in 1 point increase in SAT score. Strong correlation, indeed nearly the strongest you can get, but do we want to spend that much money for a single point in score? The latter is a policy question and not answered by how strong the correlation is. In Levitin's actual example, the 0.91 correlation is for about a 70 or so point bump per mere $1,000, which is a lot more tempting and could warrant the expense if we value 70 points that much. The Forbes graph was designed to make you think extra money adds trivial pointage. It shows near zero increase, it seems, if you don't think about the scale they chose. Levitin's corrected graph shows you the pointage increase is not trivial, but also neither is it extraordinary. His version allows an informed debate to be had over whether the actual increase in score is worth that increase in expense, whereas the Forbes version tries to convince you no debate is even to be had. Lying with statistics. In this case, by choosing a scale that makes the actual increase in SAT scores disappear from human visual acuity so that it seems to be nothing. Here's a response I gave with regard to another challenge question on correlations. If I were to draw a graph showing the number of mornings a rooster crows and overlay it with the number of mornings the sun rises in the east and got a correlation of 0.99, what error am I committing? What I'm getting at is this. Even if a graph shows a correlation of 1, how do we test to see if there is a causation between the two? Dr. Carey's response. Levitin will cover that question. It's the correlation fallacy question, but the short answer is this: you don't know by itself. There is usually a causal theory that has to be argued for with other evidence. In the SAT case, it's pretty obvious money causes SAT scores and not the other way around, though one might want to think through what causal models could lead to increasing SAT scores causing increasing expenditures. And you will know then how to check if that's the case because the model will tell you. For example, look for chronological order, let's say. The third possibility is a third factor causation. Some third factor is causing, separately, both the increases. This is actually a more serious possibility. For example, if the dollars are not adjusted for inflation, the increase could simply be an accident of time and really not increases in money. For example, if the dollars are not adjusted for inflation, the increase could simply be an accident of time and really not increases in money, but changes in technique over time are the cause. These are indeed the sorts of things scientists should be and usually are looking for, but someone keen on concealing them from you isn't likely to tell you what was found. So you are right to critically think that very question: where is the evidence for the causal model being argued for? The correlation by itself is not evidence enough, because many different causal models could explain it. Figuring out how to tell causal models of the same correlation apart is, in fact, most of what occupies science as a field.